Good morning. My name is Malgorzata Celuch. I am co-founder of QWED company. And in the MAMA project, I have the pleasure of leading QWED research team in our activities towards materials characterizations and modeling. Since majority of talks in this workshop have been focused on the characterization aspects, I would like to say a few words about the modeling and how it can be merged with materials characterization for better accuracy or new designs. Let me start with the acknowledgement. My acknowledgement to the MAMA project is natural. I would like to focus on acknowledging not just the European funding, but also our fruitful collaboration with the partners and thank the partners for the ideas which have come from this collaboration. The modeling software, which I will be showing in this presentation, is QuickWave software from QWED. And again, I would like to stress that this software is not being developed from scratch in the project, but it has been commercialized since 1997. And what we do in MAMA is extending the software with new models and procedures and finding new applications. The resonators, and specifically the split post-dielectric resonators, which will also be a focus of my talk, are based on the original designs from Professor Jerzy Krupka. And last but not least, some of the modeling concepts which I will use for material measurements come from our friend Per Wiesman dealing with microwave heating in microwave ovens. The outline of my talk. I would like to say a few words about QWED company and our basic role in MAMA. Then I would like to clarify how we understand materials in classical electromagnetics and in our modeling. Then I will look at how we measure electromagnetic properties of materials. And again, I would just like to take a look at the very fundamentals of material measurements in resonators, in quasi-free space systems, or in transmission lines and SMM. I will show how we model material measurement test fixtures in QuickWave and in the MAMA activities, and I will summarize my talks. About QWED company, I co-founded the company with my three colleagues from the Warsaw University of Technology. That was 23 years ago. Our activities can be divided into three branches, which we are always trying to combine. The first branch is electromagnetic simulation, so the main topic of my presentation today. Our research ideas dating back to 1980s have been embedded in a software which has a name QuickWave. The software has been presented in many publications and received a couple of awards. We also have material test fixtures, which come from the designs of Professor Krupka. We merge both activities in our consultancy and in the research projects listed on the right-hand side of the slide. Specifically in MAMA, we are exploring the synergies between the material measurement techniques and the modeling tools which we have in our company. If you look at modeling software, this software needs material parameters to be defined. So the material parameters must come from appropriate material databases, and these come from material measurements. Now, to perform a measurement, we need a material test fixture, which will be developed using our modeling tools. What is now classical electromagnetics and how we understand materials in electromagnetics? Being now active in the European Materials Modeling Council, I feel that our activities start where the chemical science finishes. So we start the application of our modeling and equations where a material can be considered as a continuum. So we may have many materials in our systems. They may have arbitrary boundaries, but within each elementary volume, the material parameters must be defined by appropriate relations. The whole problem is just a simple set of equations, so-called Maxwell equations, They are differential equations or integral equations. They are easy to solve in this classical problem of wave propagation in free space. That would be sufficient for many applications in radars and TV transmission. But this becomes more complicated when the electromagnetic fields interact with the different materials, and we must take material constitutive relations into account. We have different ways of modeling materials in QuickWave software. A material can be defined by its scalar parameters, permittivity, permeability, but these parameters may also be frequency dependent. They may be defined by curves, by frequency domain characteristics. They may also be defined in text files and in databases, which happens specifically in microwave heating problems, where very often the user has proprietary data of material parameter variations with temperature, for example, when heating, in this case, potato in a microwave oven. And actually, a QWED first experience and my own first experience with materials modeling was not in microwave, millimeter wave applications, not in material measurements for integrated circuits or for energy materials. It was in the microwave heating applications and in microwave oven design. You see here several examples of cases where we deal with wave interaction with a material. For example, in the lower row of pictures, you see how a wave impinging on a circular body, spherical body, which may be a neck, forms a circumferential moat around this body. And this will lead to an exploding egg effect in the microwave oven. You also see how electromagnetic waves generated by a range of antennas, sensors around a human head, form different field patterns inside the human head. And the resulting response received by the antennas leads us to microwave imaging. So what we are doing in the MAMA project is also the material imaging problem, and it also resides in capturing a response of a system to a specific material sample. How do we do it? Well, let's start with a canonic problem of a resonator. I believe resonators are the simplest structures where the concept of a material test fixture can be explained. When we consider a cuboidal resonator, a solution of the Maxwell equations can easily be obtained in an analytical form. It will be given by resonator dimensions and mode numbers, which are just consecutive natural numbers. And we will see that the frequency at which this resonator resonates is proportional to wave velocity of wave propagation in a medium filling the resonator. For a non-magnetic and lossless or low-loss dielectric, this wave velocity is inversely proportional to the square root of material permittivity. C is a constant, is the speed of light. So we see that by filling a cube or any other cavity homogeneously with a specific material and capturing the resonant responses, we directly obtain the material parameters. This looks extremely straightforward, but of course the problems come in practical applications where we need to consider the issues of coupling the energy to the cavity, of cavity losses, of machining an appropriate sample to fit into the cavity, of field pattern changes by the sample under test, and many other issues. Thus, the resonator which we at QWED use most frequently for materials characterization is a split post resonator. It is a little bit different from just a simple cavity. Indeed, it has a cavity wall around, so the orange area is a metal block conductor. White is air. Inside, we have two high permittivity ceramic blocks, ceramic posts. That's why the resonator is called split post. These posts are mounted on a low permittivity, low loss dielectric just for the purpose of mounting them to the cavity. And now we insert a sample into this area between the two posts. And just like in the case of a cuboidal cavity, we measure the tuning of a resonance. But what are the advantages of our approach? You see that the electric field is concentrated in the area between the posts, so it is concentrated in the sample. Its response to the sample will be very good, very strong. But there are low fields at the cavity walls, which means that we are suppressing any losses due to metal. I will not talk more about all the fantastic parameters of this resonator because my focus now will be on how we model it and how modeling helps in its design. So I leave the rest of the text on the slide for your interpretation. This is the design of our split post resonator in Autodesk Inventor software. It may be interesting to note that the same software is used in mechanical design. So in fact, a mechanical design, for example, of a complete car can be transferred for the electromagnetic modeling through our interface, our plugin to the Autodesk Inventor. We model our resonator with all its details, and we make two modeling runs. One is of an empty resonator, and one is of a resonator loaded with our sample. We will see how the resonant frequency and Q factor change as a result of the sample being inserted. In the software, we can take a look at how the fields are distributed in the resonator. This is a full-wave solution of the Maxwell equations, taking into account material parameters, which we assumed in this case. And we will see that the field pattern between the loaded and unloaded case differs very slightly and only around the edges. So we actually obtain a structure when the sample does not change the field patterns, and it allows us to start with very simple approximate formulae for detecting material parameters from the test fixture response. And then we make more accurate approximations in an iterative manner based on the modeling. An example of how we calibrate a resonator is shown here. We consider 3 different resonators, and we consider 3 different samples. We compare the measured permittivity and loss tangent to reference data, and we obtain very good accuracy even before calibration. This means that the resonators are highly repetitive, and actually in this set of measurements, all our resonators fit into the IEC norm, which governs the split post resonator measurements. But our calibration further suppresses the errors by an order of magnitude. So the modeling has led us to the design of the resonator, and afterwards it also helps us to obtain more accurate parameters a posteriori, taking into account any manufacturing differences between these 3 units. In this case, one of the tuning factors, calibration factors that has been taken into account is the so-called normalized energy filling factor. It depends on permittivity, epsilon of the sample, and it depends on the sample thickness. And you can see that these functions are smooth, but they are not canonical. So without a full wave solution, we would not be able to obtain this level of accuracy. The next application of the modeling, which we pursued in the MAMA project, was extending our standalone resonator measurements to a scanning regime. The left photo shows you how a measurement is made in a classical setup where we insert a sample into the resonator and observe the response on, for example, on a laptop screen if you use our QMeter, or on a VNA screen if you use a VNA. We clearly see the limitations of the maximum sample size. There will also be limitations on the resolution, on the spatial resolution. which result from the size of the head of the resonator, which is the area where we have non-zero electric field which interacts with the material. So in the MAMA project, we have first of all extended this resonator. We have built this resonator into a motorized setup. With a much larger imaging surface, we can insert big samples up to 80 by 100 millimeters, and we can scan them with a small scanning step, typically 1 millimeter step. This is, of course, much more convenient for big samples. It also allows us to perform automatic imaging of surfaces. But what do we obtain as a result? You'll see here a sample which was prepared by Materia Nova. In a part of the sample, as a result of depositing organic semiconductor, we had the name of our company deposited. And after the scanning, what we see that the image is diluted. This is because the head of the resonator, this area of non-zero field, is larger than, for example, the center of letter Q. And that's why, specifically for letters Q and D, we see an image which is inverted. We see a dark region where we would expect to have a white region of R. So we see the image, but the image is not as good as we would like it to have. What can we do? We can again resort to the modeling, and we can say that although the measured result is diluted by the resonator head, but we know exactly the field pattern in the resonator, and we can use it to deconvolve our image. Again, we apply the modeling. We see how the electric field strength varies as a function of radius, as a function of distance from the center of the resonator. We construct a matrix problem, taking a matrix of measurements and a matrix, a kernel of the transformation, and we obtain a resolved pattern, which you see on the right-hand side here. So this was the second application of the modeling in the MAMA project. Now I would like to also show that our modeling tools are applicable to quasi-free space problems like antennas, which are also used broadly for material measurements. Actually, antenna applications were one of the first applications of QWED software. The small picture on the left shows a piece of a waveguide feed, which was designed at the National Radio Astronomy Observatory. This is a NASA lab in Charlottesville in the US, and you can see excellent agreement of the measured and simulated data. We can also model and simulate full antennas. When the antennas are actually symmetrical, this modeling is particularly fast and powerful. This is an antenna used for millimeter wave measurements of materials, and here we can model structures measuring a few thousands of wavelengths inside on a moderate PC or even on a laptop. You can also see patch antenna systems, Vivaldi antenna. We can see a pyramidal horn used for military surveillance. And here again, a nice jump between the applications. We modeled this pyramidal horn antenna in the 90s for Professor Stets at the Military University of Technology. And now what we see is that this kind of antennas are popularly applied to material measurements. And actually a pyramidal horn is representative of the IMM system which has been implemented at adamant premises. So what we model here is not strictly the IMM antenna, for which we did not have the exact dimensions, but this is the antenna that has been designed by my former students at the Warsaw University of Technology using our software. This is the photo of the antenna. in front of the simulation, showing us how waves exit from the horn and how a wave propagates in space. There is also a lens which helps focusing the energy at a sun. We see how the reflection coefficient at the input of the antenna varies as a result of, for example, sheet resistance of a composite or as a result of a small defect of a composite. Interpretation of this data can be performed again with data treatment or with further inspection of the modeling results. So what I'm just showing here is the applicability of our modeling tools to these kind of problems and also extreme efficiency. The next application to the modeling test fixtures will be naturally the application to SMM, which was a hard technology for the MAMA project. We collaborated very closely with our colleagues from ETH, and we compared quick wave modeling in 2 dimensions for a circularly symmetrical structure. We can reduce the modeling to just a long section of the problem. And we correlate the FDTD modeling in quick wave. These are the rectangular meshes which you can see on the left picture, with finite element modeling, which was developed during the MAMA project at ETH. You see that the field patterns at a specific frequency agree very well. In both cases, we also see that the reflection coefficient simulated at the input to the SMM in both cases agree very well, and also the response to materials corresponds to what we physically expected. So this was a canonical problem of a simple, just a tip, an SMM tip. And now we have performed full 3-dimensional modeling of probes from IMN and METAS. So here is the simulation of the IMN probe. You see the geometry of this probe with mesh as used in our software. You see the electric field pattern at the feet of a strip line, and you see the electric field at tip at different frequencies from 1 gigahertz to 110 gigahertz. All these fields are very efficiently obtained with quick wave tools. We have also analyzed a probe from METAS. At the first side, the geometry of this probe looks actually symmetric, but we cannot apply the 2-dimensional modeling because the problem which we want to solve is a corner of a rectangular gold patch. And we want to place our probe at different points around the corner of the sample. The modeling is performed in a region of 100 by 100 micrometers. The raster between the simulation points, the points at which the probe is placed, is 25 micrometers. And you can see example sets of curves. According to our colleagues from METAS, all these results make sense, and this is what has been expected. In conclusions, in the MAMA project, QWED team has performed extensive modeling of a variety of material measurement test fixtures. In this presentation, I have shown you examples of resonators, antennas, and SMM. We also modeled coaxial probes, and we also considered and modeled many different resonators not shown in this presentation. Quick wave has also been enriched with many models and procedures necessary either for the accuracy or efficiency of our modeling of material measurement test fixtures. What's important is that accuracy of our modeling is equivalent to classical problem-tailored approaches. And the advantage of using this general purpose software is that it opens way to new test fixtures, and it also allows us to improve accuracy based on more extensively obtained data sets. The modeling is being promoted and collaborations are thought through the European Materials Modeling Council and also in IEEE. For more results of our modeling, please visit our website, and there is also an open platform section within our modeling results where versions of our software are available for free download with the purpose of dissemination and also education in the areas of the MAMA project. I would also encourage you to look at QWED software on the same website and at a brochure summarizing the technical results concerned with our measurement test fixtures. Thank you for your attention.